Hello students. In this session, we are going to do problems on magnetic moment, then magnetic field due to magnetic dipole and Coulomb's law. Okay, Coulomb's law in magnetism. Okay, all these things we will cover. Okay, so this session, okay, problems on magnetic moment, magnetic moment, then magnetic field. Okay, could be due to a pole or magnetic dipole, magnetic dipole. Okay, all these things we shall try to cover. So okay, then Coulomb's law. So we will cover problems of all these in this session. Okay, so as a quick recap, I shall say magnetic moment is what pole strength into the distance between the poles. Okay, if it is given as L, we can take directly M into L, but generally as a convention, we used to take this length. If when we consider magnetic dipole, this we used to consider as 2L. Then due to a bar magnet on the axis, what is the magnetic field? 2K M divided by R cube. Okay, then on the equatorial point, this is equal to what? Km divided by R cube. Okay, then Coulomb's law is what? F is equal to K m1 m2 divided by R square. So let us try to cover these things. Okay, so here comes our first question. Two identical thin bar magnets, each of length L and pole strength M, are placed at right angles to each other, with the n pole, north pole of one touching the south pole of the other, with the north pole of the north pole of one touching the south pole of the other. Find the magnetic moment of the system. Find the magnetic moment of the system. So suppose if we consider a magnet like this, okay, another magnet is kept at a right angle. Another magnet is kept at a right angle with the north pole, okay, touching its south pole. Okay, so this is north pole, this is south pole of respective magnets. Find the magnetic moment, resultant magnetic moment. So this is going to be the magnetic moment of this first bar magnet, and this is the magnetic moment of the second bar magnet. They are all identical. So magnetic moment due to first one and moment due to second one, both are same, and the resultant is going to be at a 45 degree because both are same. Okay, now what is the resultant magnetic moment? M resultant is going to be what? They are vectors. Magnetic dipole moment is vector. So root of what? M square plus M square. So this is going to be root 2M. Root 2M. And what is the value of M? Root 2 into the pole strength into their length is given as L. This length is given as what? L. So M into L. So root 2 ml is the answer. So here option B is the correct answer. Clear? So this can be kept at any angle. Here it is 90 degree. It can be kept at 30 degree, 180 degree. So magnetic moment, one thing which we need to consider here, it is always, if this is south pole and this is north pole, take the direction of magnetic moment, dipole moment, from south to north, just like we take from positive charge uh, to negative charge. Okay, sorry, negative charge to positive charge. If we take minus q and plus q, the dipole moment, okay, electric dipole moment is going to be what? P. Okay, same way here, this is from south to north. Clear? Hope it is clear. We will move to the next problem. Okay, next problem is calculate the force acting between two magnets. Okay, two magnets of length d each and pole strength m each. When the separation between their north poles is d and the separation between the south poles is 3d. Okay, two magnets are kept. The distance between their north pole is d, separation between the south pole is 3d. Okay, so let us consider like this. If this is a magnet, okay, so separation between them is also same as the length of the magnet. Suppose if this is n, okay, and this is n, and then obviously this distance can be d. Okay, if this is south pole and again this is south pole, this distance can be considered as what? 3d. Okay, now it is fine. Now we need to find the force acting between two magnets. So there are four poles here, two south poles, two north poles. So whatever, suppose if we consider this as the first magnet and this as the second magnet, the force on one due to two and force on two due to one both will be same. Just we are applying exact Coulomb's law here. So we will try to find one force that will be same for all of them. So force on one due to two, we will find force on first one due to two. Okay, so this is S1, this is N1, this is N2, and this is S2. Okay, now first we will find force on N1 due to N2. Force on N1 due to N2. So what is this? Force is equal to what? Force is equal to K into M1 M2 divided by R square, the distance between them. This is the general formula. So we will apply that formula here. K into, okay, their pole strengths are same. So K M square divided by the distance between N1 and N2 is D. So D square. Now whether it is force of attraction or repulsion, this is going to be repulsion. So we are finding the force on 1 due to 2. So on this N2, the direction of force is going to be this. Let us take here negative. Okay, left side we will take it as negative and the right side we will take it as positive. Okay, so that is done. Now next one, force on S1. Okay, south pole 1 due to N2. Okay, due to N2. So this is also K M square divided by. So force on S1 due to what? N2. So that distance is how much? This distance is also what? D. So this is going to be, the distance is 2D and this is all square. And force on S1 due to N2 will be what? Attractive. So let us keep it as positive because this force will be in which direction? In this direction. This force is in this direction. So that is done. Now what? Force on S1, force on N1, force on N1 due to S2. Force on N1 due to S2 will be what? Km square divided by force on N1 due to S2 is actually again 2D distance, 2D whole square. And what will be the direction of that force? Direction of force will be attraction towards right side. So that is also positive. Clear? Now next one, force on S1 due to S2. Force on S1 due to S2. So Km square. What is the distance between them? Now this is 3D and all square and repulsive also. Repulsive also. So this direction is the force. So there is attractive force and repulsive force. All of them are in a left and right directions. So we need to find the net force. Let us take here. So F net is equal to what? Minus km square by d square plus km square by 4d square plus km square by 4d square. One was minus. What was that? Km square divided by 9d square. So what we will do? We will take km square by d square outside. And this is going to be what? We will take LCM. This is going to be 36. LCM is 36. And this is going to be minus 36 plus 9 plus 9, and this is going to be minus 4. So we will be getting km square divided by d square into, this is going to be minus 40 plus 18. So minus 22 divided by 36. So negative is coming. So whichever negative, which is nothing but repulsion. Negative means repulsion. Okay, that is how we have taken. So km square divided by d square into 11 divided by what? 11 divided by 18. 11 divided by 18, and this is going to be repulsion. Okay, okay, so 11 by 18 km square by d square, and that is repulsion. Option A is the correct answer. Okay, so these are the options. Clear? Hope you understand. Okay, note down the solution. Okay, students, hope you understood the solution. Okay, first page, and this is the second page. Okay, now we will move to the next problem. Yeah, this is the next problem. So two like magnetic poles of strengths 5 ampere meter and 20 ampere meter are situated 1 meter apart. Okay, magnetic poles. At what point on the line joining the two poles will the magnetic field be zero? So just like we have done charges, we keep two charges separately, negative charge and positive charge, and in between there will be a point where force will be zero, electric field will be zero. Those kind of situations we have seen. So exactly same way this question also. Okay, so let us consider two magnetic poles. They are of same type, maybe north and north or south and south likewise. So this is M1 and M2. Okay, both are north and north, we will assume, and their strengths are also given 5 ampere meter and 20 ampere meter. They are separated like this. Okay, 1 meter apart. At what point on the line joining the two poles will the magnetic field be zero? So here, suppose if we consider magnetic fields will be away from the north pole, let us consider 3 points, points outside and inside, where there is possibility for it to become zero. So suppose if I consider this point, okay, and then this point somewhere in between, between in the sense between, anywhere between M1 and M2. Okay, so P, Q, R, 2 points if we consider. Okay, then at P, see, B1, the magnetic field due to M1 will be B1 away from it. Due to B2 also what? Away from it. Now, if we consider R, due to M1, B1 will be away from it, and due to M2, B2 that is also away from it. So there is no possibility that it is going to be zero because they are in both that same direction. Here, B1 will be away from it like this, and due B2 also will be away from it, both in the opposite direction. So the possibility to become zero is only at Q. Okay, so we will solve now. Okay, so this is M1 and this is M2. Okay, let us consider a point which is X distance from M1. And since this is 1 meter apart, both are 1 meter apart, the other side is going to be 1 minus X. This is the distance. Okay, so now at this point, the net magnetic field is 0. Okay, and B1, B2 like this. So B1 must be equal to B2. Okay, now what is B1? K m1 divided by x square. What is force? Force is equal to, just like kq by r square, we are going to have here km by r square. K here, it is nothing but mu 0 by 4 pi. In the case of electric field, we know this is 1 by 4 pi epsilon 0. So same way here. And this is equal to what? Km2 divided by 1 minus x the whole square. So m1 is given as 5 by x square, and this is going to be 20 divided by 1 minus x square. So 1 minus x the whole square. Okay, 1 minus x the whole square. Okay, so here 1 minus x the whole square divided by x square is equal to what? 20 by 5, and 1 minus x by x, if we take, this will become 2. So 1 minus x is equal to 2x, and we will be getting 1 is equal to 3x, and x is equal to what? 1 by 3, or 0.33 meters away from M1. Okay. Okay, so let us see the options. So 0.66 from 5 ampere meter pole, no. 1.66 wrong. 0.33 meter from 5 ampere meter pole towards the 20 ampere meter pole. That is the correct answer. Correct or what? Look at this solution. Okay, clear? Okay, so here the answer is going to be option C. Okay, clear? Shall we move to the next problem? Okay, next problem is two short bar magnets of magnetic moments 96 ampere meter square and 81 ampere meter square are placed along mutually perpendicular straight lines meeting at a point P. Find the magnitude and direction of magnetic field at a point P if it lies at a distance of 0.4 meter and 0.3 meter respectively from the centers of two magnets. Okay, so I shall consider two magnets. Okay, so one magnet, they are kept mutually perpendicular. See, they are kept mutually perpendicular. So kept like this, mutually perpendicular, mutually perpendicular straight lines meeting at a point P. So this is the point where, okay, this is the point P. Okay, two short bar magnets of magnetic moments 96 ampere meter square and 81 ampere meter square are placed along mutually perpendicular straight lines meeting at a point P. Okay, straight lines are meeting at the point P. Find the magnitude and direction of magnetic field at the point P if it lies 0.4 meter and 0.3 meter distant. Okay, so suppose if we consider this as 0.4 meter, and if we consider this distance as 0.3 meter respectively from the centers of two magnets. Now we need to find the magnetic field. So we can understand that for both of them, the point P is nothing but axial point. Okay, I am considering this as south pole, this as north pole, this as south pole, this as north pole. Even if we change the poles, whatever way we want, if we put, this is not going to make differences. Okay, you can take anything. I have taken like this. Okay, so point P. Now, what we shall do if we consider this is one, the direction of one magnetic field due to this first one, and if this is second one, the magnetic field direction will be like this. So this is due to second one along axial direction, this is due to first one along axial direction. Now, uh, see, one is 96 ampere meter square. So here, this one's magnetic moment is 96 ampere meter square, and this one M2's magnetic moment is how much? 81 ampere meter square. So now we will calculate each one, then we will find the resultant. So B1 axial point. So what is the formula? K2 km divided by r cube. So this is going to be what? 2 into mu 0 by 4 pi into this one's magnetic moment is 96 divided by 0.4 the whole cube. Okay, so this is going to be 2 into 10 raised to minus 7 into 96 into, now this is going to be, I shall write this as 4 into 4 into 4. This will become 10 raised to minus 3, that I shall put here. So if I solve this, okay, if I solve this, I will be getting 3 into 10 raised to minus 4 Tesla. Okay, 3 into 10 raised to minus 4 Tesla. Now, B due to 2, that 2 at the axial point is equal to what? 2 into mu 0 by 4 pi into 81 divide by 0.3 the whole cube. This is equal to what? 2 into 10 raised to minus 7 into 81 into 10 raised to 3 divide by, this is going to be 3 into 3 into 3. So if we solve this, we will be getting 6 into 10 raised to minus 4 Tesla. Clear? Now we will take the angle, sorry, we will take the resultant. Okay. The resultant magnetic field is going to be what? Root of, they are mutually perpendicular. So let us take 3 into 10 raised to minus 4 the whole square plus 6 into 10 raised to minus 4 the whole square. A square plus B square plus 2AB cos theta. Cos theta is 90 degree. Cos 90 is 0. So we don't write that part. So 10 raised to minus 4, if we take outside, this is going to be what? 9 plus 36. We will be getting 10 raised to minus 4 into root of, this is root 45. Root 45 is what? 9 into 5. 9 into 5. So we can write like a 3 root 5 into 10 raised to minus 4 Tesla. 3 root 5 into 10 raised to minus 4 Tesla. 3 root 5, 10 into 10 raised to minus 4 Tesla. Option D is coming as the correct answer. Okay, direction is not asked here. So why? Because we have the freedom to take, yes, south pole, north pole, south pole in the way we want. So since it is asked only the resultant values, whatever poles we take, okay, it does not cause any differences. Anyway, both magnetic fields are going to be in 90 degree at a mutually perpendicular direction, and you will be able to solve. Okay, so please look at the solution. Okay, so hope you understood. Okay, we will move to the next problem. So here, two short magnets P and Q are placed one over another with their magnetic axis mutually perpendicular to each other. Magnetic axis means nothing but south north. South north. If this is the bar magnet, magnetic axis is this south and north. Okay. Okay. It is found that the resultant field at a point on the prolongation of the magnetic axis of P is inclined at 30 degree with the axis. Okay, compare the magnetic moments of the two magnets. Okay, magnetic moment of P and the magnetic moment of Q will have to compare. Okay, so let us consider. Okay, this is one magnet, short magnet. I am just drawing as bigger one. Okay, and another magnet is kept like this. Okay, so this is one magnet, this is another magnet. Okay, so this is south and this is north. Okay, two short magnets P and Q are placed over one another with their magnetic moments mutually perpendicular to each other. So if I keep like south here, north here, and see, this will be the magnetic moment of P. Okay, so they are mutually perpendicular to each other. It is found that the resultant field at a point on the prolongation of magnetic axis of P, this is P and this is Q. Okay, so magnetic axis, if I prolong on prolongation of magnetic axis of point of P, so that is inclined at a 30 degree with the axis. So here we can see the resultant magnetic field. The resultant magnetic field is like this. Okay, so this is at an angle of 60 degree. Okay, with the axis. That is what they have said. Okay, so now how we need to compare the magnetic moments. So the thing is, now that point P, if I consider the point P, that point P is actually axial point for P magnet. Okay, let us take some other letter here. Okay, let us consider. Okay, X. Okay, so at the point X, the magnetic field is axial magnetic field, or this point is axial for magnet P and equatorial for magnet Q. Correct or what? Here, this is the magnetic moment. Okay, so that is how. Now, if we consider like this, if this is going to be the axial point for which one? P. Axial point for P. Okay, axial point for P, and this point is equatorial point for Q. So for point Q, because of Q, the magnetic field, that is equatorial point, is going to be in this direction, in the south direction. You might be remembering, at equatorial point the direction of magnetic field was this. Even electric field was also same way. Okay, so same way, this is how. So this is due to Q and this is equatorial point. So formula for this one is nothing but 2km divided by r cube, and this is going to be what? Km divided by r cube. Okay, and this is due to P and this is due to Q. And this distance from the center, because center of both of the magnets are uh, same. Okay, because they have kept over one another with the magnetic axis mutually perpendicular. Okay, so we can consider this distance. This is same for both the things. Okay, now okay, this angle is not 60. I have written here 60. This is 30 degree. Okay, 30 degree. What this is given in the question. Okay, 30 degree. 30 degree. Now if we take the direction, this is BQ equatorial. If we take the direction, we can say tan 30 is equal to what? A B magnetic field due to Q divided by magnetic field due to P. And if I substitute the formula for both, I will be getting due to Q, what is this is equal to K magnetic moment of Q divided by R cube. This divided by 2k into magnetic moment due to P divided by R cube. So tan 30 is 1 by root 3, and this is equal to what? Mq divided by 2mp. So if they are asking, like in the options you can see mp by mq. So mp divided by mq is going to be what? Root 3 by 2. Root 3 by 2. So which option is correct? Option D is the correct answer. Is that clear? Okay, so please note it down. So these are some of the standard questions which is testing our knowledge on uh, magnetic dipole moment, the magnetic field due to bar magnet at equatorial point, axial point, its resultant direction, all these. Okay, so hope you understood the thing. We will see some more problems in one another session. Hi students, uh, here in this session we will do some problems on work, torque, and potential energy. Okay, torque, then work, potential energy. Okay, all related to what? A bar magnet. Okay, so in from the chapter magnetism and matter, we deal with a bar magnet. Oh, okay, so when we deal with the bar magnet, the rotation of bar magnet, its torque and work, potential energy, all these things we will have to understand. Okay, so we will do that. So what is torque? The formula for torque is M cross B, or MB sine theta. M is magnetic dipole moment or magnetic moment. B magnetic field, sine theta. Theta is the angle between magnetic moment and magnetic field. What is work done? Work done is equal to MB cos theta 1 minus cos theta 2. Okay, then potential energy is what? Minus MB cos theta. Okay, so these are the things which we will see now. Okay, so moving to the question. So first question is, a bar magnet has poles of strength 48 ampere meter which are 25 centimeter apart. What is the magnetic moment of the magnet? So first question is that. So what is magnetic moment? Magnetic moment is pole strength into the distance between them. So pole strength is given as 48 ampere meter. The distance between the poles, okay, is given as 25 centimeters. So 25 into 10 raised to minus 2. Okay, so this is equal to what? 48. 48 into 25. Okay, so 48 into 25. Uh, okay, this is equal to what? 12 ampere meter square. 12 ampere meter square. That is the first question. Okay, fine. Next question is, what torque is required to hold this magnet at an angle 30-degree with a uniform field of flux density 0.15 Tesla. So here they have given like a magnetic field is going to be 0.15 Tesla. That is what is flux density means, magnetic field only. Okay, so 0.15 Tesla. So flux density is actually flux per area. That is nothing but magnetic field only. What torque is required? See, in this question, suppose if we directly find out torque, okay, you pause the screen and find out. Pause the screen and find the answer for this question, and please ready with the answer. Okay, please do this. Okay, hope you have completed. So you might have done in this way. mb sine theta. So magnetic dipole moment 12 into magnetic field is there into what, sine 30 you might have done. In the options they are going to give clockwise as well as anti-clockwise. You might have got zero point 0.9 Newton meter answer you might have got. So options they are going to give, this is going to be clockwise 0 0.9 Newton meter, anti-clockwise then some other values also will be there. So here what they are asking is what torque is required to hold this magnet at the angle. So this is like suppose if this magnetic field is like this, if this is the magnetic field, okay, they have given like we need to keep hold this magnet, okay, at an angle. If this is south and this is north, okay, this angle as 30-degree we will have to maintain like this. So if this is a pole, definitely there will be a force F is equal to, just like QE, we are going to have here pole strength into, not dipole moment, pole strength into B towards right direction, and in the south pole we are going to have MB in this direction. So torque will be towards which direction in order to make it into 0 degree. So to maintain at this, then definitely we will have to apply a force in this direction so that there should be a same and opposite torque should be present. So if this torque, that is torque due to magnetic field, okay, torque due to magnetic field, how much is that? This is going to be mb sine theta. So torque is equal to mb sine theta. So what is m? M is going to be 12, b is going to be 0.15, and this is sine 30. So 12 into 0.15 into 1 by 2, if we do, we will be getting 0.9, and this direction is going to be what? Clockwise direction. So this is going to be 0.9 clockwise. So in order to maintain this at 30-degree, we will have to apply external torque. So that torque should be what? 0.9 itself, but in the direction anti-clockwise. So option 0.9 Newton meter in the anti-clockwise direction will be the answer. Okay, clear? Hope you understood. How we are taking here 30-degree? You may have the doubt that why can't we have north here, south here? When we say this data, that is to hold this magnet at an angle 30-degree, the angle of magnetic axis is nothing but with respect to magnetic dipole moment. So look, take magnetic dipole moment, then take the magnetic field, whatever be the angle, that is what we need to take here. Okay, clear? Next problem. Okay, a bar magnet with the poles 25 centimeter apart and pole of strength 14.4 ampere meter rests with its center on a frictionless pivot. It is held in equilibrium at 60-degree to a uniform magnetic field of induction 0.25 Tesla by applying a force at a right angle to its axis. Okay, 12 centimeter from the pivot. Okay, calculate the force. Suppose if the magnetic field is present like this, then what they are saying is a bar magnet, it is held in equilibrium at 60-degree. So this is the bar magnet. This is held in equilibrium at 60-degree. Okay, so this is 60-degree. Okay, and this is with its center on a frictionless pivot. So it is rotating with respect to center. Okay, now this magnetic field is given as 0.25 Tesla, that is also there. Okay, now this is at equilibrium. Okay, so what are the forces available at this point? There will be a force This force is what? F is equal to what? Mb. And here there will be another force. Here also F is equal to what? Mb. Okay, so both the force in opposite direction. And they are saying like it is held in equilibrium to a uniform magnetic field of induction 0.25 Tesla by applying a force at a right angle to its axis. At a right angle to its axis. So this is the axis. Okay, 12 centimeter from the pivot. So somewhere here there is a force in this direction, and this direction, this is 12 centimeter from the pivot. This much data is given. We need to find the force. It is in equilibrium, so we can say that this is in rotational equilibrium. Rotational equilibrium. Okay, or we can say tau net is equal to 0. Okay, net torque is equal to 0. So that is nothing but the torque in clockwise direction should be equal to torque in the anti-clockwise direction. Clear or what? So we can say torque due to magnet, that is magnetic field. The torque due to magnetic field should be equal to the torque in the anti-clockwise direction, or the external torque we can say. Okay, so now we will equate them and we will find the force. Torque due to magnetic field is what? Mb sine theta. Okay, and torque due to that external force will be what? Force into the perpendicular distance. Force into the perpendicular distance. That is force. Here perpendicular distance is 12 centimeter. Correct. So equating all of them, this magnetic moment is nothing but m into 12. M into 12. So let us put everything. M into 2l into b into sine theta is equal to what? Force into the perpendicular distance. Okay. Now here the pole strength is given as 14.4. 14.4 into what is the length of the magnet? It is given as 25 centimeter. The poles are 25 centimeter apart. So this is 25 centimeter into magnetic field is how much? 0.25 Tesla. Okay, into sine 60. So root 3 by 2. This is equal to force into that perpendicular distance is actually 12 centimeter. Correct or what? This force is applied at 12 centimeter. So 12 centimeter we can take. Okay. So if we solve them, just solve this. If we simplify this, we will be getting around 6.5 Newton. So everything is available, only we need to simplify this. Simplify in such a way that easily we need to simplify, okay, just by cancelling the values. Clear? So somewhere around 6.5 Newton will come. Option A is coming as the correct answer. Clear? Okay, please copy this, note it down. Okay. Moving to the next problem. So calculate the work done in rotating a magnet of magnetic moment 3 joule per Tesla through an angle 60° from its position along a magnetic field of strength 0.34 into 10 raised to minus 4 Tesla. So what is work done? Work done is MB into cos theta 1 minus cos theta 2. So calculate the work done in rotating a magnet of magnetic moment. Okay, magnetic moment is 3 through an angle of 60° from its position along the magnetic field. So initially, suppose if this is the magnetic field, from its position along the magnetic field. So this was the position, south, north. So from this, it is changed to what? 60 degree. Okay, at 60 degree. So B is given as 0.34 into 10 raised to minus 4. Initial position is nothing but cos 0. Final position is nothing but cos 60. So cos 0 is 1, cos 60 is 1 by 2. So 3 into 0.34 into 10 raised to minus 4 into what? 0.5. Simplify this, we will be getting 0.51 into 10 raised to minus 4. So this could be written as 5.1 into 10 raised to minus 5 joules. Option A is the correct answer. Okay. Okay, so we have touched problems from the parts we have studied from the magnetic moment, bar magnet fundamentals and all. Okay, so practice more number of questions and make your concepts very strong. Okay, students, thank you so much.